Alright, welcome back, ladies and gentlemen. In this video we're looking at forces for the first time, and so there's several things we're going to look at. First of all, types of forces. We will look at a number of examples that are going to give us different types of forces. We will learn how to draw forces in what's called a free body diagram. Sometimes you'll see FBD for short, right? And one last thing, and this is going to be really intense, really cool, is we're going to compare the acceleration that an object experiences to the mass of the object. We're going to see what we can learn from that comparison. So that's going to be in this video. There's a lot we're about to get started with. Here we go. So basically, what is a force? A force is real simple. It's a push or a pull. That's it. At its simplest definition. There you go. Now, what do we have to know about forces? Well, if you're going to push or pull on something, what you end up doing is changing its motion. So forces change motion. Very important idea. Very important idea. But we're going to modify this idea a little bit. I want to add a word to this phrase, and so we make it a little more accurate for all situations here. So let's say unbalanced. You'll see unbalanced forces change motion. That is the better way of saying this, the new and improved way. So you definitely want to remember this. Absolutely. Absolutely remember that. Unbalanced forces change motion. Well, what does that imply? That if you have balanced forces, you will not change the motion. Oh, by the way, what are we talking about with changing motion? Well, if you have a change, no, not an A, oh, sorry. I want that, you want a triangle. If you have a change in the motion, motion is velocity, then you must have an acceleration. So if we have unbalanced forces, they change motion, then unbalanced forces produce accelerations. If you observe that there is no acceleration, then you can conclude there must be balanced forces only. Either no force or all the forces are balanced if there is no acceleration. Okay, well, great, we have the basics, but what sorts of forces are there that we could encounter, that we could be dealing with? These forces come under two different, very broad, very general categories. Contact forces and field forces. So contact, holy cow, I can spell. Contact forces. And another category called field forces, we'll get to that in a moment. Well, for contact forces, there has to be physical contact, literally. Okay. What's an example? You could have an applied force. And the symbol for applied force, you might just use an F or say F applied. And, well, for example, you get that kind of force when you take an object and you push it with your hand. Well, you've applied a force to it. Okay. What else? We could have some sort of support force. Okay. Now, support force is caused by contact with a surface, and there's a special name for that. It's called the normal force. Normal force. Literally, that's what you need to call it. And so if you have an object sitting on a surface, well, it's hard to see because the surface is going to push up on this object, straight up, sort of at you, and that's called the normal force. and the symbol is Fn, like that. By the way, the symbols I'm using, they're not absolute. Other textbooks, other teachers might use different symbols, and that's okay. Another force is going to be the force of friction. It's a very important force. You don't ever want to ignore friction unless you're told that it's okay. Now, friction is a force that occurs between two surfaces that are in contact. You know, you got one surface and another surface, and they're in contact, and there's either motion or there is the tendency to move, like it wants to move. And friction opposes the motion, always opposes motion, or that opposes the tendency to move, right? So we're not going to get into the details of friction right now, but for now, we can say F sub F as a way to write it. There's a type of force called drag, where it's basically friction with a fluid. So, friction. Now, a fluid is either a liquid or a gas, such as water or the atmosphere or something else. If you want to represent drag, FD, like that. You could have tension as a force. Not muscular tension, not drama. We're talking about tension in a rope, a chain, a string. This kind of force only pulls. It does not push. You could represent force of tension, F of T, F sub T, like that. And one more I want to mention. We're not going to deal with springs right now, but there is such a thing as a spring force. And actually, it's very, very important in many ways. Spring force. I'll use the word force. This is interesting. There's more going on here. This can push or pull, depending on how you're dealing with it. So, oh, pardon me for that noise. Got a spring. And if you compress the spring wants to push back outward. Or if I stretch the spring wants to pull back in. So springs could push or pull depending on how you look at it. And what happens is, well, let's not get into the details. It's actually kind of intense when you start to study springs. What we could do for now, if we have a spring, call it F sub SP for spring. And this is by no means all of the possible forces. It's just a few very common ones. Now there's the other category called field forces. And this might sound weird at first, but field forces don't require contact. Something doesn't have to be touching the other thing to affect it. Well, the obvious one, the common one, is a gravitational field. That's what we mean by field forces, a gravitational field. The weight of an object is caused by a gravitational field. So it's like weight, or the weight is the force. And it's really important, actually. It always acts down. Or you might say toward the center of a large body, like the Earth, or the Moon, or the Sun. Okay, gravitational field is a field force. There are others that we're not going to study right now that won't be part of what we're doing. But you could have an electric field. You could also have a magnetic field. And an electric field, well, charged particles like protons or ions, charged atoms, could be electrons also. They generate electric fields. Magnetic fields, well, of course, you have magnets. And these two are weird because what they do is they can either attract or repel. They pull or push, it depends, right? Because, you know, with magnets, You get a north and a south pole together or near each other, and they'll attract. So opposites attract. If you get two north poles, it'll repel. Electric field, kind of the same way. If you get two positively charged particles, they will repel each other to get a positive and a negative nearby, and they will attract. Gravity is weird. Gravity sucks. Literally, it only ever sucks. It pulls in. It doesn't ever repel. It doesn't push things apart. It's strange that way. But that's okay. Gravity is the one we're going to deal with quite a bit. Quite a bit. And it's possible we'll get to the other two, one of the other two likely, later in this course. So those are types of fields. Sorry. The weight. How do you represent the weight? Let me make sure you get that. Typically F of G, force of gravity. That is equal to the weight. Okay, wow. A lot of information, but this is stuff you want to be very familiar with. You want to be able to use the terms, friction, drag, tension. You want to be able to use the symbols, force of friction, normal force, force of friction, force of drag, and write these symbols, force of tension, in a diagram, as you'll see. Check it out. Here we go. How do you diagram this? How do you draw this to represent it? Represent these forces. What you're going to do is you're going to draw what's called a free body diagram. FBD for short. So I want to show you something here. If I have a textbook resting on a table. I know some of you are saying it's the same example I used in class, and well, you're right, but watch. I told you I was going to improve things. Here we go. Here's a textbook. We know the textbook has weight. And we know that the table supports the book. It's a support force. And we know now what we should call that. That is a normal force. Now, why do you call it a normal force? The reason is that this force, this support force, is always normal to the surface where there's contact. Normal means at right angles. This force is always at right angles to that surface. So, if we had a tilted surface, then the normal force would tilt also. Okay, remember that. That's what normal means. Now I want a free body diagram this guy. X and Y axes. Label those. Dot. Okay. Weight down. Force of gravity. And normal force up. Now my question to you is, how do I know how long to draw these arrows? How do I know that they should be the same length? Well, of course, you say. Mr. Woods, it's obvious. This book has no acceleration. And you told me just a few minutes ago that if I observe no acceleration, then I have balanced forces. If I do see an acceleration, then I must have unbalanced forces. Okay, so you observe no acceleration, therefore forces are balanced, and that means I have to draw them equally. Yes, good job. Let's look at one more example here of a free body diagram. It's going to be a water skier accelerating across the water. Okay, marker's starting to go. So here's my situation. Water ski and water skier. And of course there's a rope, and the rope goes to a boat, and the boat is actually, what's getting the skier to accelerate across the water. Brilliant. We have an acceleration in that direction. Now what are the forces acting on the skier? So here we go. The skier has weight. The water is providing a normal force to the skier. The rope is applying some tension. Force of tension to the skier. And there's one more thing. I don't know if you would be aware of this, but the water itself is sort of sliding past the water ski. And when it does that, it creates a force. There's drag. Force of drag. It's like friction with the water. Yes. So we can represent four forces here. Okay, I have to draw the free body diagram now. This is not a proper free body diagram. Let's create one. So a free body diagram, remember, it represents the system that I'm concerned with, because I want to isolate that system from the rest of the universe. Nothing else matters. In this case, my system is just the water skier. Not the rope, not the water, not the boat, just the water skier. In this case, the system was just the book. So what I do is I'm going to draw a dot. I didn't explain this over here, I'm sorry about that. A dot that represents that object. And I'm going to draw forces as arrows. And the longer the arrow, the stronger that force is. And the direction of the arrow tells me which direction the force is acting. That totally matters. These are vectors. Vectors have direction, and they also have size, sometimes called magnitude, right? Okay. I observe an acceleration to the right. Yes, that's important. That acceleration is not in the y direction. It's not up and down. I observe no acceleration up and down. So my up and down forces have to be balanced. They have to be equal. So here's normal force, there's weight. Now, the tension and the drag, the force of tension, force of drag. Oh, these are left and right. These are in the x direction, so I have to remember I want to produce an acceleration to the right. I have to keep these two forces unbalanced. So which one needs to be bigger? You're absolutely correct. The one that needs to be bigger is the one to the right, in the direction of that acceleration. There's a force of tension. So I have to draw the drag smaller than that one. There's force of drag. And so look, this is critical. Okay. No acceleration in the y direction or up and down, because those forces are balanced. These two forces are not balanced, and so they lead to this acceleration to the right, because the force to the right is stronger. It's a little bit like a tug of war, right? And the one that's stronger wins. And so that is a proper free body diagram of the skier. This is a proper free body diagram of the book. And there you go. Free body diagrams are generally pretty easy once you have identified the forces. Once you've done this work, that's easy. This can be the hard part sometimes, but there will be more practice coming your way. Now, there's one more thing to get to in this video, and it's really, really cool, but also rather important. Let's look at weight for a second as a force. Okay. We're going to consider this force of weight caused by a gravitational field. I'm going to stop using this guy. I think he's done. Now, we know that gravity accelerates all objects at 9.8. So little g is 9.8 meters per second squared. And that's true of all objects when there's nothing else affecting the object. That's called free fall. You remember that condition, right? So if I have something, I just drop it. Well, it will accelerate downward at little g. There's a weight, and the weight is what's pulling it down, accelerating it downward. Well, what I want to do is I want to consider different masses, different objects. So let's say I've got 50 grams. There actually is a 50 printed on that one. Let's maybe consider 100 grams. Let's consider 200 grams. Let's consider 300 grams. All right, there's a 300 right there. Let's consider a 500 gram mass, and even a 1,000 gram mass. This is 1,000 grams, 1 kilogram. Okay, I'll get these back out of the way because I really don't need them on the paper. I just wanted to show you. And so what I want to do is I want to say, well, is there some sort of relationship between the acceleration that these masses would experience if I dropped them? Between the acceleration they experience and between the mass. We're going to compare. Remember, g is gravitational acceleration, and mass is just going to be kilograms. So we're going to be comparing them. Do we see something between the 50 and the 100 gram masses? They will accelerate downward at the same rate. They would hit the ground at the same time. But is there something we can learn? So what I want to try doing, check this out. I'm going to make a graph. And I'm going to graph the acceleration that these things experience versus the mass that they have. And let's see what happens. Well, the mass that's pretty straightforward. I've got the 50. And so on this scale, I've got 2 lines and then 0.1, 0.2, 0.3. This is kilograms. And so where would 50 grams be? Well, that's actually right here. That's 0.05 kilograms. There's 50. That would be 100 grams. That would be 200, 300, 400, 500 grams. And therefore 1,000 grams is right there, 1 kilogram. So I can plot my masses on this. I'll have some empty space that I'm not using right now. That's fine. And then acceleration. Now the acceleration we're dealing with is little g. It's 9.8. Oh, so it's just that. Watch this. 9.8. Let's see, this is 5, 6, 7, 8, 9, 10. So 9.8 is like there. Right? Line, just so I can label that. 9.8. And that's meters per second squared. And now, let me see what I have to do. Well, this is interesting because they'll all have an acceleration of 9.8, won't they? So the acceleration will be a constant value. Let me get a line drawn here. There. A little too close on this end, sorry. That red line is my acceleration of 9.8. That's little g. Little g equals 9.8. And that doesn't matter what the mass is. So this 50 gram mass is going to accelerate at the same rate as this 200 gram mass, and the same as this 500 gram mass, and the same as this 1,000 gram mass. They will all accelerate at the same rate. Well, what gives here then? Well, something interesting is going to show up here. We're going to do a little trick with this graph that we've seen before. In kinematics, when we were looking at motion, we saw that sometimes the area under the line of a graph, so this area, could tell us something. Can it tell us anything here? Well, I have acceleration from there to there. This is value of acceleration. And I have mass from there to there. So if I want to find the area, I have to multiply a length times a width, right? That's because this looks like a rectangle, yeah? If I just kind of imagine an imaginary line right there. That's a rectangle. I want the area. It's length times width. There we go. Length times width. What's my length? My length will be mass. My width is here to here. That's going to be acceleration. Okay, is this going anywhere? Well, what is my acceleration? My acceleration is little g. So I have m times g. Well, okay, but so what about that? What would the units of m times g become? Oh, the units of m are kilogram, and the units of g are meters per second squared. It's an acceleration, right? And so when I deal with that, what I find is a combination. You combine those into a kilogram meter per second squared. All right. Well, this is pretty cool, but it's cumbersome. And so what physicists have figured out is a new name for this. They call it a Newton. Why call it a Newton? Well, after Sir Isaac Newton. Sir Isaac Newton, one of, if not the really greatest physicists of all time. intelligent beyond belief, beyond imagine. He was involved with physics. He was, I'll say, he shared responsibility for the invention of calculus. He didn't invent the telescope. It had been invented well before his time, but he designed a new kind of telescope. He helped improve them. He did a lot of work with optics and with figuring out what light really is all about. But anyway, enough of the history. We call this thing a Newton, or capital N, and now I'm sorry about this, that capital N is a Newton, but this capital N is normal force. You just have to get used to that, okay? Fn is normal force, just a capital N by itself is a Newton, and you'll usually see this with a number in front of it. And so that'll tell you that that's a Newton instead. That's a unit of force. That's what we're looking at here. Check this out. Why do we see this? What's going on? Well, let's take the 100 gram mass. It's this thing, and there's 100 grams, and it will accelerate at 9.8. But what does the area under the graph for 100 grams look like? Well, it's this area. Okay. And if I had two of these, well, then I would have 200 grams. And what would that area look like? Well, the area would be twice as large. And what we're finding, since we have this new thing we can talk about, and the new thing is force. We're finding, literally, it is weight, though. It is very specific. This thing is 200 grams. It doesn't accelerate down any different than this one, which is half of the mass. Well, why not? Because this one is being pulled half as hard as this one. The amount of pull downward on your 100 grams is half as big as the amount of pull downward of your 200 grams. They weigh different. The 100 grams is half the weight. You can tell, just kind of heft them in your hands. You can tell one is heavier. If you're really careful, you might guess that one is twice as heavy if you didn't know the numbers. The 100 grams has half the weight of the 200 grams. It's being pulled with half the force. That's why the smaller object accelerates at the same rate as the larger object. It's being pulled half as hard as that guy is. It's very interesting how this works. What about the 500 gram mass? Well, right there, how much force is there on that guy? It's all of this force. The 500 gram mass is being pulled with 5 times the force as the 100 gram mass. And finally, the 1,000 gram mass. All of it. All of that. That's being pulled with 10 times the force of the 100 gram mass. It's 10 times heavier. It has 10 times the weight. Okay. So that's what I wanted to show you about weight. It turns out all forces, not just weight though. So I want to clarify this for you, because I want to step away from weight. All forces are measured in newtons. Capital N for newtons. Okay. And it also turns out that the acceleration an object experiences does not have to be 9.8. So acceleration could be 9.8 meters per second squared. It doesn't have to be. It could be anything else. Acceleration could be 1. It could be 2. It could be 17,000. I mean, whatever you need. And this is really interesting. So look at this. We have mass times acceleration. Let me switch colors here so it stands out just a bit. Purple. Kilograms is mass. Meters per second squared is acceleration. Mass times acceleration gives us what? It gives us a force. Force equals mass times acceleration. F equals ma. This is an equation that you really need to be comfortable with. You need to get used to it. Now, it's a little misleading, and I'll wrap this video up with this. This almost looks like when you have a force and you multiply by the acceleration, you get the force. Did I say force? I'm sorry. Let me start over. When you have the mass and you multiply by the acceleration, then you get the force. Now you can calculate the force that way, but it sounds odd because the force is not the result of the acceleration. It's the other way around. The force causes the acceleration. So it's actually handy from time to time to rearrange this and say that the acceleration is equal to force divided by mass. Because it's the force acting on the mass that caused the acceleration. The acceleration is the result of the force acting on the mass. But that's a real important equation. We're going to use that a whole bunch coming up in the next few days. All right, that's all for now. This has been a huge amount of this video already. Thank you for watching. I'll catch you next time.